Hello everyone, welcome back to the course Vector Calculus and Complex Analysis. Myself Dr. N.CH.Ramgopal, working as Associate Professor in Mathematics in the Department of Humanities and Sciences, MLR Institute of Technology, Hyderabad. Today I am going to discuss some problems on poles and residues. So, pole and residue at that pole. In the last session, we have discussed important definitions on singularities, different types of singularities, then definition of pole, residue at that pole, etc. Now, pole is one type of singularity. So, it is also a singular point that follows some particular definition. Now, how to find these poles? There is another thing called zeros of a function f of z and poles of a function f of z. To find the zeros of the given function, equate the numerator to 0. To find the poles, equate the denominator to 0. So, first we find the poles by equating the denominator to 0, and then we calculate the residue at each and every pole. To find the residue, there are two ways. One is using the Lorentz series expansion, and also using the standard formula. Here, if a pole z equal to a is a non-repeated one, then it is called a pole of order 1. So, which is called a simple pole. For example, if this pole is repeated m times, then it is called a pole of order m. So, to find the residue at a pole of any order, for example, z equal to a is a pole of order m, then the residue can be calculated, residue of f at the pole of order m is calculated using the formula 1 by m minus 1 factorial limit z tends to a, that pole, d power m minus 1 by dz power m minus 1, that means m minus 1th order derivative of z minus a power m into f of z. So, this gives the residue of the pole z equal to a of order m. Even you can find the residue of a function f of z at a simple pole, that means pole of order 1 also, using the same formula. Put m equal to 1 here. So, you can find the residue of residue of f at a simple pole. Today we are going to find the residues using this standard formula. Let us solve some problems on the same. Now, the problem number 1. Find the poles and residues of f of z equal to z square by z minus 1 into z minus 2 whole square. So, coming to the solution part, the given function of complex variable is z square by z minus 1 into z minus 2 whole square. Now, first we need to find the poles. How to find the poles? By equating the denominator to 0. Z minus 1 into z minus 2 whole square is equal to 0. So, this is z minus 1 is 0 or z minus 2 whole square is 0. That implies z equal to 1 and z equal to 2, where 2 is a repeated one. So, therefore, z equal to 1 is a simple pole. Here, z equal to 1 is a simple pole, and z equal to 2 is a pole of order m, where m is 2, pole of order 2. Now, to find the residue at the simple pole z equal to 1. Now residue of f at z equal to a is given by, if a is a pole of order m, then m minus 1 factorial limit z tends to a d power m minus 1 by dz power m minus 1 of z minus a power m, because a is a pole of order m, z minus a power m into f of z. Here simple pole, that means z equal to a equal to 1 and m equal to 1, because it is a simple pole. Then residue of f at the simple pole z equal to 1 is given by 1 by 0 factorial, which is 1, limit z tends to 1. If you put m equal to 1 here, d power 0, so that means no need to find the derivative for a single pole, for a simple pole. So z minus a into f of z. So limit z tends to 1, this is z minus 1 into f of z is z square by z minus 1 into z minus 2 whole square. So here this z minus 1 gets cancelled, and the limit as z tends to 1, the answer is 1 by 1 minus 2, which is minus 1 whole square. So the answer is 1. Similarly, we can calculate the residue of f at the second pole, which is 2, z equal to 2, which is of order 2. Now residue at the pole z equal to 2, and here m equal to 2, because it is repeated twice. It's a pole of order 2. So the formula is limit, so residue of f at z equal to a is 1 by m minus 1 factorial, limit z tends to a d power m minus 1 by dz power m minus 1, that means m minus 1 the derivative of z minus a power m into f of z. So here m equal to 2. So residue of f at z equal to 2. So a is 2 and m is also 2. So 1 by 2 minus 1, which is 1 factorial, limit z tends to a is 2 here, and m equal to 2, so d by dz remains, and z minus a whole square into, what is the function f of z? F of z is z square by z minus, so here also a is 2, so z minus 1 into z minus 2 whole square. So here these two gets cancelled. So this is limit z tends to 2, the derivative of z square by z minus 1. So this we need to calculate. Here we use u by v rule. Denominator whole square, denominator into numerator derivative minus numerator into denominator derivative, which is 1. Now if we apply z equal to 2 here, so 2 minus 1, 1 into 2 into 2, 4 minus z equal to 2 minus 4 by 2 minus 1 whole square, which is 0. Therefore, the residue at the pole z equal to 2 is 0. Similarly, let us solve another problem. Here we need to find the poles and residues. So f of z is z e power z by z minus 1 whole cube. Here z equal to 1 is a pole of order 3. Here by equating the denominator to 0, what we get? Z minus 1 whole cube is 0. So z minus 1 is 0. Z equal to 1 comma 1 comma 1 3 times. Now if z equal to a is a pole of order m, what is the formula to find residue? At z equal to a is 1 by m minus 1 factorial d power m minus 1 by dz power m minus 1 z minus a power m minus m into f of z. So here z equal to a equal to 1 is the pole and the order is 3, so m equal to 3. Substituting this, the residue of f at z equal to 1, which is a pole of order 3, 1 by 3 minus 1 factorial limit z tends to 1 d power 2 d power m minus 1, which is d square by dz square of z minus 1 whole cube into f of z. So what is that f of z? Z e power z by, so 1 by 2 factorial limit z tends to 1 d square by dz square, that means the second order derivative of z minus 1 whole cube into z e power z by z minus 1 whole cube. These two gets cancelled and we need to find the second order derivative of this z e power z, and then we apply the limit as z tends to 1. So this is equal to half into limit z tends to 1, the first order derivative of z e power z. So half into limit z tends to 1 d by dz of UV rule. Here we need to apply UV rule because both the functions are having z. So z into derivative of second function e power z plus second function into derivative of first function 1. And again we need to differentiate this. So first let us simplify this, d by dz of e power z into z plus 1. Now again differentiating half into limit z tends to 1, again UV rule, the first function into derivative of second 1 plus second into derivative of first is e power z. Now we have to apply the limit as z tends to 1, e power z common, then z plus 2. So this is equal to half into apply z tends to 1. So e power 1 into 1 plus 2, 3. So 3 by 2 e or 3e by 2. Similarly, let us solve one more problem. Here, find the poles and residues of f of z equal to e power z by z square plus pi square. So again, to find the poles, first we need to equate the denominator to 0. Z square plus pi square is 0. So z square is minus pi square. So z is plus or minus I pi. So therefore the poles are z equal to minus I pi and z equal to plus I pi. Both are simple poles. Simple poles. That means m equal to 1. So to find the residue of f at z equal to minus I pi, let us find the residue at z equal to minus I pi. So both are of order 1, simple poles. No need to differentiate that z minus a power m into f of z. So simply we can find the limit as z tends to minus I pi, z minus a power into 1 by into f of z. So here limit z tends to minus I pi, z minus a. So here z minus, so plus I pi, that becomes plus I pi into f of z, e power z by z square plus pi square. So to simplify this, first we need to write this function z plus I pi into e power z by, this can be written as z square minus I square pi square. So which is in the form of a square minus b square. So we can write it as a plus b into a minus b, z plus I pi into e power z by z plus I pi into z minus I pi. So these two cancel. Now apply the limit as z tends to minus I pi. So e power minus I pi minus 2I pi, and we have e power I theta is cos theta plus I sin theta. So using that, this can be written as cos I pi minus I sin I pi by minus 2I pi. So this is, we know that sin n pi is 0, so this becomes 0, and this is cos I pi by with minus sign 2I pi, and this is equal to minus 1 by 2I pi. Similarly, to find the residue of f of z at z equal to plus I pi, again we can continue the same process. We need to apply the limit, or else simply replace I by minus I. So in the final answer, so this is minus 1 by 2 minus I pi. So this is, this minus gets cancelled, 1 by, or this minus 1 can be written as, we can write it as I square, minus 1 is I square into minus 2I pi. So this I gets cancelled, so minus I by 2 pi. So like this, we find the poles and residues of the given function. Let us solve one more problem. Find the poles and residues of f of z equal to sin square z by z minus pi by 6 whole square. So here f of z is sin square z by z minus pi by 6 whole square. So to find the poles, let us equate the denominator to 0. Whole square is 0. So z minus pi by 6 is 0. Z equal to pi by 6 is a pole of order 2. So therefore here m equal to 2. Now residue of f at this pole z equal to pi by 6 is given by 1 by m minus 1 factorial, 2 minus 1 factorial, limit z tends to pi by 6, d by dz of z minus pi by 6 whole square into f of z, sin square z by z minus pi by 6 whole square. So these two gets cancelled. Now this is 1 by 1 factorial, which is 1, limit z tends to pi by 6, the derivative of sin square z, just the first order derivative. So limit z tends to pi by 6, the derivative of sin square z is 2 sin z into inner function derivative cos z. So which is limit z tends to pi by 6 sin, which is in the form of 2 sin theta cos theta, which is equal to sin 2 theta. So sin 2z. Apply the limit as z tends to pi by 6, 2 into pi by 6. So which is sin pi by 3 root 3 by 2 is the residue of the given function at the pole z equal to pi by 6. Coming to the last problem, here find the poles and residues of whole cube. So here to find the poles, equate the denominator to 0. Z square minus 1 is 0. Z square equal to 1. Z is plus or minus 1. And here both Z equal to 1 comma minus 1 both are poles of order. Here we have 3 of order 3. So therefore M equal to 3. Now to find the residue of F at Z equal to 1, which is of order 3, is equal to 1 by 3 minus 1 factorial m minus 1 factorial limit z tends to 1 d power 3 minus 1. So d square by dz square of this at z equal to 1. What is the pole here? So which is of order z minus 1 power 3 of z square minus 1 power 3. Now again here we need to simplify this. So 1 by 2 factorial limit z tends to 1, the second order derivative of this z minus 1 whole cube by the inner function, this z square minus 1 can be written as z plus 1 into z minus 1 whole cube. So 1 by 2 limit z tends to 1 d square by dz square of z minus 1 whole cube into 1 by this one z minus 1 whole cube into z plus 1 whole cube. These two gets cancelled. So we need to differentiate this 2 times. So d by dz of first time derivative, d by dz of z plus 1 power minus 3. So half into limit z tends to 1 d by dz of minus 3 into z plus 1 power minus 3 minus 1. So by z plus 1 power 4. Now again differentiating half limit z tends to 1. So which can be written as half limit z tends to 1 d by dz of minus 3 z plus 1 power minus 4. So this is again this minus 4 minus 3 into minus 4, which is 12 into z plus 1 power minus 5. So half into, let us apply z tends to 1. So 12 by 2 power 5. So this is 6 times here, 6 by 32. So 3 by 16. Similarly, we need to calculate corresponding to the pole z equal to minus 1 also. Now, residue of f of z at z equal to minus 1. So, which is 1 by 2 factorial limit z tends to minus 1 d square by dz square of, now z tends to z equal to minus 1 is the pole now. Z plus 1 here z minus 1 whole cube. Now z plus 1 whole cube into what is the function? 1 by z square minus 1 whole cube. So 1 by 2 limit z tends to minus 1, the second order derivative of z plus 1 whole cube 1 by z plus 1 whole cube into z minus 1 whole cube. So these two gets cancelled, and now we have to differentiate twice. So the first time derivative of z minus 1 whole power minus 3, half into limit z tends to minus 1 d by dz of, this is minus 3 z minus 1 minus 4. So again here half into limit z tends to minus 1, this is 12 into z minus 1 power minus 5. So half into 12 by z minus 1 minus 1 minus 1 or minus 5 plus 5. So this is 6 times here, 6 by minus 2 power 5. So minus 6 by 32. So minus 3 by 16. So like this, we can find the residue of the function at a pole using the standard formula. So today we have solved some problems on poles and residues. How to find poles? By equating the denominator to 0. How to find residue at the corresponding pole? Use the standard formula using which we can find the residue of a pole of any order m. So this is for today's session, and in the next session we are going to find the residues using the Lorentz series expansion, and that is the actual definition. The residue at a pole is the quotient of 1 by z minus a in the Lorentz series expansion. So those problems will be discussed in the next class. Thank you very much.